So, welcome to the class. And in our second unit of work, heat, and the first law of thermodynamics, we will discuss three terms in this lecture: internal energy function, mathematical formulation of first law, and a differential form of first law. In last class, we had the concept of internal energy function and the physical interpretation of that function. Now we can have. And in last class, we have derived this equation W I to F adiabatic equal to UF minus UI. That means adiabatic work equal to change in internal energy. And this was our derivation. And the physical interpretation of the difference UF minus UI is the increase in internal energy of the system. Then the equation W I to F adiabatic, that means work done during adiabatic process, equal to UF minus UI expresses the law of conservation of energy. From this equation, it is clear that there exists an energy function whose difference between two values is the energy change of the system. The internal energy is a function of as many thermodynamic coordinates as are necessary to specify the state of the system. We have mentioned that you can represent a thermodynamic system using a number of thermodynamic coordinates, and those thermodynamic coordinates are sufficient to represent the internal energy, and internal energy is a function of those thermodynamic coordinates. The equilibrium states of a closed hydrostatic system can be completely determined by any two of three thermodynamic coordinates P, V, and T, since the third is fixed by the equation of state PV is equal to RT. This we have mentioned. We have the equation PV is equal to nRT. So, if you can represent your thermodynamic system with the P, V, and T, so only two is necessary because the third one is fixed with this equation PV is equal to RT or PV is equal to nRT. That means suppose you know P and V, you can find the value of T. That means only two are independent variables. Therefore, the internal energy is a function of only two. That means any two. That means either PV or PT or VT of the thermodynamic coordinates. And the exact form of the function is unknown. That means U as a function of this, there is no direct equation for that. But since we need only a difference in internal energy, it is not necessary to know the exact form. And this is an important concept. For an ideal gas, U is a function of temperature alone. That is, U is a function of T alone. So, in general, you will consider U as a function of P and T as well as V and T. This is a basic method. In case of a hydrostatic system, if U is regarded as a function of T and V, then the change in internal energy you can write as our U is a function of T and V. Therefore, du function of T and V can be written as du by dt at a constant volume into dt plus du by dv or du by dv at a constant temperature into dv. This is a general way of writing an exact differential equation that is known to you. And regarding U as a function of T and P, you can similarly write as du by dt at a constant pressure into dt plus du by dp at a constant temperature into dp. And you can view these two. This is du by dt and this is also du by dt. But this is at a constant volume and this is at a constant pressure. And one should realize that the two partial derivatives, du by dt at a constant volume and du by dt at a constant pressure, are not equal. The first partial derivative is a function of t and v, and the second is a function of t and p. And they are mathematically different and have different physical meanings. And next is the mathematical formulation of the first law of thermodynamics. And with our knowledge of the internal energy function, now we are trying to derive the mathematical formulation of first law of thermodynamics. And this we have already mentioned. A system can undergo a change of state through the performance of adiabatic work alone. That we have seen. Also, the change can take place non-adiabatically. Two examples of such processes involving changes of state that take place adiabatically and non-adiabatically are depicted in the figures given below. And you can see that this is an adiabatic wall, all sides, this is a gas. So, this can expand or you can compress it. That means the system can interact with its surroundings by the performance of work, and that type of work we have already mentioned as adiabatic work. And here you can see that adiabatic wall, adiabatic wall, adiabatic wall, but this is a diathermic wall. That means you can increase the temperature of the system by placing a Bunsen burner. That means you can heat it, and when you can heat it, this piston can expand. That means it can perform work. So this is a way of non-adiabatic work, and this is adiabatic work. So you can see that in figure A, that means this one, a gas is allowed to expand adiabatically. And this is in figure B, the gas is heated with the Bunsen flame, and at the same time it is allowed to expand. You can see the differences. Let us now imagine two different experiments performed on the same system. That means you can consider this as the system. The same, these two same, you have a same system, and on that system you are performing adiabatic process as well as the non-adiabatic process. In the first experiment, we measure the adiabatic work necessary to change the state of the system from I to F, and this is UF minus UI. This is already known to us. In an adiabatic work or adiabatic process, adiabatic work equal to change in internal energy. In the other experiment, the system is subjected to the same change of state non-adiabatically, and the work required is determined. It can be seen that non-adiabatic work is not equal to UF minus UI. That means you are first noticing that non-adiabatic work is not equal to adiabatic work, because adiabatic work equal to UF minus UA. That is, non-adiabatic work and adiabatic work are not same, they are different. And your adiabatic work equal to UF minus UI, and non-adiabatic work is not equal to UF minus UI. That means the change in internal energy function. And in order to satisfy the law of conservation of energy, that means a system is going from an initial state to final state, that change will be always same. So that energy is conserved, or you can have, that means the change in energy is same, but that change in energy is converted as work. or work is converting as energy here. That is your work energy principle. So there should be some missing link terms when the two functions are not equal. So how can you balance that? So we are forced to conclude that energy has been transferred by means other than the performance of work. In adiabatic work, you can say that adiabatic work has converted as internal energy. If work is done on the system, energy has been increased. When you are performing work non-adiabatically, that means you are performing some work. You assume that that work you can consider as less than the adiabatic work. But you are getting the same change in internal energy. So, which means that this is mechanical way of transferring energy. That means some energy has been transferred between your system and surroundings non-mechanically or other than by the performance of work. That means some energy has been entered the system, and due to that your energy has been increased. So some energy has been entered, and you can assume that suppose that the work you are performing is greater than adiabatic work, but you are getting the same thing. That means some energy has been left the system. That also you can say. So this energy you are calling as the heat. That means energy that is transferred between system and surroundings non-mechanically. Mechanically means that is a performance of work or other than the performance of work. And you can simply understand that when it is an adiabatic system, no transfer of energy is possible. That is why your work done is always equal to your change in internal energy. And this transfer of heat takes place only by virtue of temperature difference between the system and its surroundings. When a diathermic work is done, that means work done which is not adiabatic, that you are calling as a diathermic work, that means energy transfer is possible between system and surroundings. When a diathermic work is done on a closed system whose surroundings are at a different temperature, then the energy transferred by non-mechanical means is equal to the difference between the change of internal energy and the diathermic work. This difference is called heat. That means you can write as Q is equal to UF minus UI minus W diathermic. In the previous case, you just compare, there W adiabatic was equal to this one. That is why this Q is equal to 0. But here Q is not equal to 0. That is why UF minus UI minus W diathermic equal to Q. Or you are writing it as UF minus UA equal to Q plus W. And this Q is positive when heat entered, and the quantity about Q, you are assuming that Q is positive when heat enters the system and negative when heat leaves the system. That is the convention of Q. Heat entering the system is positive, heat leaving the system is negative. And the convention for work is non-negative. Work done on the system positive, work done by the system negative. Similarly, heat entering into the system is positive, heat leaving the system is negative. And this equation UF minus UA is equal to Q plus W is known as the mathematical formulation of the first law of thermodynamics. It should be emphasized that the mathematical formulation of the first law of thermodynamics contains three related ideas: the existence of an internal energy function, the principle of conservation of energy, that means based on that you have derived this equation, and the definition of heat as energy in transit by virtue of temperature difference. And next is the differential form of first law. A process involving only infinitesimal changes in the thermodynamic coordinates of a system is known as an infinitesimal process. For such a process, the first law becomes du equals d bar q plus d bar w. We have already written this term d bar w. So, this shows an inexact differential, and D means it is exact differential. Exact differential means it depends only on the initial and final points of and not on the path. It is a point function and not a path function. And when it is inexact, it depends on the path. It depends on the path. That is why you are considering it as inexact. Du equals d bar q plus d bar w. Heating and external work done do not depend on the thermodynamic coordinates of the system. Heating, or simply you can consider as heat. Heat and external work do not depend on the thermodynamic coordinates of the system. So d bar q and d bar q are inexact differentials. So this u, which is exact differential, it depends on the thermodynamic coordinates. So you can write as u is a function of t and v, or t and p, etc. But you can't write q as a function of t and v, t and p, etc. Similarly, that for work also. And for a hydrostatic system, now you can write this first law of thermodynamics as our differential form is du equals d bar q plus d bar w. And for infinitesimal quasi-static process of a hydrostatic system, you can write this d bar w, that means work done as minus pdv. And on substituting that, du equals d bar q minus pdv, or d bar q equals du plus pdv. Here it is d bar q, I'm sorry, where u is a function of any two of the thermodynamic variables pv and t, and this p is a function of v and t from the equation of state pv equals nRT. And now we can apply the first law of thermodynamics for different cases. Our isothermal process, and for isothermal process you can say that du is equal to 0. And how it is possible du is equal to 0 for isothermal process? We have mentioned that for ideal gases, you can consider u as a function of temperature alone. That means when there is no change in temperature, there is no change in u. That means your du equals 0. And first law of thermodynamics is du equals d bar q plus d bar w. And you can write this d bar w as minus pdv. That means your du, in place of du, you are writing as 0. 0 equals d bar q plus d bar w, or d bar q equals minus d bar w. So in this process, heat supplied is completely utilized for doing external work. And now adiabatic process, and in this process you can write d bar q equal to 0. And our first law is du equals d bar q plus d bar w, and this d bar w you are writing as minus pdv. So du equals d bar q as 0 plus d bar w, or du equals d bar w, or you can write du as minus pdv. So in adiabatic compression, work done is positive. That means work done on the system. That means when you are compressing a gas, that means adiabatically your work is done on the system. That means this equation d bar w is positive. So this is also positive. This is positive. This is positive. That means temperature increases. So when du is positive, which means that uf minus ui is positive. That means uf is greater than ui, and u is a function of temperature. So if uf is greater than ui, which means that temperature has been increased. And during adiabatic expansion, work done is negative. That means work is done by the system. So this is negative. So du is also negative. That means uf minus ui is negative, or uf less than ui. That means temperature decreases. And this is based on this concept, our U is a function of temperature. And next is isobaric process. And here, as we know, for isobaric process, P is a constant, pressure is a constant, and our first law of thermodynamics is du equals d bar q plus d bar w, and this d bar w you are writing as minus pdv. So du equal to d bar q minus pdv, or d bar q is equal to du plus pdv. So in this case, the heat supplied to the system is used for two purposes. One for increasing the internal energy and hence the temperature of the system, and the other for doing external work of the system. So the heat given to a system is utilized for increasing the internal energy and for doing external work when it is an isobaric process. And for isochoric process, our volume is a constant, and this is our first law, du equals d bar q plus d bar w, or you can write du as d bar q minus pdv. And at a constant volume, that means isochoric process, this dv is 0, since v is constant, so du equals d bar q. So in this case, the entire heat supplied is used for increasing the internal energy and hence the temperature. That is, heat is the flow of internal energy in an isochoric process. So next is cyclic process. As you know, cyclic process, after a series of processes, the system is coming back to its initial conditions. So here you can say that du equal to 0 because your u is a state function, and in a cyclic process, after a series of processes, the system is coming back to its initial conditions. That means ua equal to uf, and our first law of thermodynamics is du equals d bar q plus d bar w. Du is 0, so 0 is d bar q plus d bar w, or d bar q equal to minus d bar w. And in this process, heat supplied is completely utilized for doing external work. And this is similar to your isothermal process. And this concept we are normally using in engines or heat engines. And that's all in this class. So we will discuss some related ideas regarding this first law of thermodynamics in our next class. Thank you.